I'm Nick T, short for Ty. Okay, chapter 11, review thing here on momentum. Quite a bit. Let's get this thing started. So we talk about the idea of momentum, and we have to understand what inertia is first, because inertia has to do with the resistance of a physical object to any change in its velocity. This could be direction of motion, it could be to the object's speed itself. So when we start looking at what are some obvious examples, okay? Because momentum really is the measure of that object's inertia. Its resistance to changing its movement, its speed, its direction. So if you're strapped into your car and you're driving toward a light, a stoplight, and the light's green, but then it changes to red, you step on the brakes, your car comes to a hard stop, your car stops, but you feel that going a little bit forward, your body moves forward. That's inertia. That's the resistance to the change in the motion of your body. You see, the brakes resisted the change. They resisted your car not to go forward any further. Your seatbelt prevents you from flying through the windshield. Okay? Inertia has to do with how that resistance that the object has to changes in the speed, which could be speeding up or slowing down, in this case slowing down, or the direction. So when we look at momentum, the unit of momentum is kilograms times meters per second. So in other words, mass times velocity. So when we look at something like this here, okay, a soccer ball with a mass of 1.5 kilograms traveling at 5 meters a second, or a baseball with a mass of 0.5 kilograms traveling at 10 meters per second, that's just simply multiplying it through. 1.5 times 5 gives us 7.5, that's our original momentum, and then here we have a 5 that equals our momentum. So the soccer ball that has a mass of 1.5 kilograms traveling at 5 meters per second has a greater momentum compared to our baseball that is traveling. Is it possible for two objects to have the exact same momentum? Yes. Even if the objects are weighing differently, if the lighter weight object travels faster at a faster velocity, yes, it can match an object here. Okay. So when we talk about momentum can change, but it's the velocity that changes, velocity over times acceleration. So force is equal to mass times acceleration. Our net force is equal to the change in momentum over the change in time. This is how Newton described inertia. Okay, so P is equal to mass times velocity. That's how we prove that the formula for momentum is mass times velocity or inertia. Okay? We talk about the idea of impulse. Now, impulse is the product of the force and the time. The force in this case is what's being exerted, what's being used. Okay? So we look at impulse as equal to the summation of all the forces times the change in time. But we know that the change in momentum is equal to all the forces times the change in time. So when we look at the change in momentum, that is our impulse. Okay, I is equal to the change in momentum. Okay, the momentum at the beginning, the momentum you have at the end. That's the impulse. Okay, all right, let's move on here. All right, so we talked about a 60-kilogram paratrooper jumping to the ground from a plane 500 meters high. The instant he hits the ground, the velocity is 6.26 meters per second downward. After he lands, his velocity is 0. So what's the change in momentum? Well, originally you got 60 grams and 6.26 meters per second. So that's our initial velocity, our initial momentum. So I can look at PI is equal to the mass of our paratrooper times the initial velocity of our paratrooper. So that's going to be 60 times 6.26. Okay? Now, here's the thing. Since the final momentum is 0, the change in momentum is whatever 60 times 6.26 is going to be. Okay, so 60 times 6.26 equals, so it's a change in momentum, 375.6 kilograms times meters per second. Now, there we go. That's our change in momentum. If he hits the ground flat-footed with his knees locked at 0.100 seconds, what's the force on his feet? Okay, so here's the thing. Now you're looking at the stopping time. Okay, so force is equal to the change in momentum over the change in time. Okay, as we saw earlier. So it was 375.6 divided by, well, what's the time? 0.1 seconds. So we get a force of 30,756 newtons that land on his feet. If we turn around and say, hey, it takes longer to land, so divide by 0.8, and we walk away with 469.5 newtons. So this is how you do it. You take your momentum, your change in momentum, divided by the change in time. The time that it took for 0.1 seconds is a lot harder on his feet than it is when it takes a little longer on there. Okay, I do need to move on. Okay, so that we already went through. Okay, we already did all this. So let me talk about conservation of momentum. We talked about Newton's laws of motion there. There's an equal and opposite reaction. And in this case, the conservation of momentum is observed. A rifle firing a bullet and the rifle recoils backwards. Okay? So the conservation of momentum, that means the resulting of all those outside forces acting on a system is zero. The linear momentum of the system remains constant. So the bottom line is the mass of the gun times the velocity of the gun is equal to the mass of the bullet times the velocity of the bullet. So P is going to equal 0 on this. A quick example of that, if I have a mass of a gun that's 1 kilogram and I have a velocity of 1 meter per second, okay, well actually, let's do this. We don't know how much the gun is going to go backwards because that's what's called a recoil. The mass of our bullet is 0.5 kilograms, that's a pretty hefty bullet, but the bullet is going out at 1 meter per second, which is pretty slow for a bullet. Okay, so when we look at that, we'll have mass of gun times velocity of the gun is equal to the mass of the bullet times the velocity of the bullet. So this is what we have. Okay? So when we're looking at that, ladies and gentlemen, we notice that we have 1 times x is equal to 0.5 times 1. So 1 times x is equal to 0.5. X is equal to 0.5. So the velocity of our gun is going to be 0.5 meters per second backwards for the gun. That's it. Okay, let's move on. Okay, so we already went through that. Okay, collisions. When we look at collisions, ladies and gentlemen, because I'm trying to pay attention to our timing here, remember that collisions are transfer of momentum between objects in relative motion resulting from their interaction. So there's 3 kinds of collisions: elastic, partially elastic, and inelastic. Now, elastic, only the conservative forces act, the total mechanical energy is conserved. Air molecules colliding, billiard balls colliding, those are about the closest example that we're going to get. The reality is that eventually these will stop moving, because in an elastic collision, there is no loss of energy, there is no loss of velocity, okay? If you've got billiard balls that crash into each other, they'll just keep going. But we know that's not true because eventually they do slow down because of friction. But they are the closest that we have. Partially inelastic collisions, okay, the things that crash into each other, they can change, they can deform in shape. But the masses rebound away from collision. So you can think about bouncing a basketball on the court. Or how about a baseball being hit with a bat, or a softball being hit with a bat? Okay, those you could say are partially elastic collisions. Okay, there is a loss. Some of the kinetic energy goes to work, the elastic potential energy, thermal energy, sound energy, or other non-mechanical energy. So there's some things that are being lost. They're being not lost in the sense of they're gone for good, they're useless, but they change into other kinds of energy, like thermal energy or sound energy. Think about the bat hitting the ball, the basketball hitting the floor. So there is that. We looked at inelastic collisions where the colliding masses will stick together as one piece. We know that kinetic energy is not conserved. We know that. Okay? So when we look at perfectly elastic versus perfectly inelastic, this is a pretty good illustration for that. Okay? We go into elastic collisions. And we have these formulas here that work out, all right? So let's go ahead and let's work on a couple of these. So two 50-gram gliders are on an air track. One glider has a velocity of 2 centimeters per second to the right toward the other glider, which is stationary, not moving. What are the velocities of the gliders after collision? Okay, so there's some things that we need to look at. We have a mass 1 and a mass 2. Okay, because we have two cars, two gliders, they both weigh the same. Okay, glider 1 has an initial velocity of 2 centimeters per second. Number 2, glider 2, okay, its initial velocity is 0. Okay, so now we got some numbers here. Now we can do a little bit of figuring out. So what do we have here? So M1 and M2 both equal 50 grams. V1I, our starting velocity of our first car, is equal to 2 centimeters per second. And V2I is 0 because it's not moving. Now, these formulas here, one tells us what's the final velocity of our car 1, glider 1, and our final velocity of glider number 2. Now, if you look, it looks very messy, but it's not too bad because we have V2I in both of these. So since V2I is 0, we saw that, this cancels out. So now there's 0. That leaves us working with these formulas. Now, let's look at V1 final. It says mass 1 minus mass 2 divided by mass 1 plus mass 2. Well, wait a minute. They're both the same mass. Mass 1 minus mass 2, guess what? That's 0. So what does that tell us about the final velocity of our first glider? It's going to be 0 meters per second. It comes to a stop, which means that its energy has been given over. Its momentum, its resistance to change has been given over. Take it, glider number 2. Take it and run. Run, glider, run. So now we're down to this formula here. So here we've got 2 times the mass of our first glider, which is 50 grams. So, okay, I'm going to put that over here. 2 times 50 divided by mass 1 plus mass 2. So that's 50 plus 50. Now all this is going to be multiplied by 2 for our original velocity. So 100 divided by 100 is going to equal 1, right? Because 2 times 50 is 100. 50 plus 50 is 100. So our final velocity, this is going to equal 100 over 100 multiplied by 2. So we end up getting a big whopping 2 centimeters per second for velocity of the final velocity of glider number 2. That's it. Okay, I've got to erase. Now remember, if there's something you're not getting, pause, go back, and try to work with that again, okay? Now there are some other example problems here as well. Now, here as we go through, here's an unequal elastic collision that I will do with you guys. Okay, so we have an out of control 100 kilogram freshman skater. Hey, the freshman's like over 6 feet tall, with a velocity of 10 meters per second north, crashing into a 10 kilogram stationary parking lot cone. What are the velocities and momentums of the skater and cone after they collide elastically? Okay. Hint, this is a two-part problem. First, we got to find the final velocities. Then we can use P equals mv for the momentum of our individual pieces, our skater and the cone. Okay, so what do I know? I know that this is mass 1. This is mass 2. This is initial velocity of 1. Okay, and this happens to be the initial velocity of 2. So now I already got my pieces here, ready to go. And oh look, that stationary parking lot cone, it's not moving. See where the zeros go into our formula? So I can eliminate this, I can eliminate this. Wow, I just saved myself a bunch of work. Wow, okay. So now let's take a look at these. So for this one here, notice mass 1 times mass 2. Unlike the other problem, they are not weighing the same. So mass 1 minus mass 2. So that's going to be 100. Why is it doing that weird thing? Okay, so it's 100 minus 10 divided by 100 plus 10. So that gives us 90 over 110. And we're going to multiply that by 10, because that's the 10 meters per second. So we're going to have our final velocity here. Like I said, I got to keep going. So we're 90 divided by 110 equals, okay, times 10 equals, so I have a final velocity of 8.2 meters per second. This is for the skater. Okay, let's look at our final velocity for our cone. It's 2 times the mass of the freshman. Oh, that's going to be, so it's going to be 200 divided by 110. It would make sense that our cone is going to travel a little faster. So 200 divided by 110 equals times, again, the initial velocity of our freshman, and that gives us 18.2 meters per second of our cone. Okay, so that's what we have. That's our final velocities. Now we can go ahead and figure out what our momentums are. Okay, so 100 grams, because remember, kilograms, sorry. 100 kilograms times 8.2 is equal to, then we have 10 kilograms multiplied by 18.2 equal. So we're going to check out the momentums here. We got to wrap up, guys. So 100 times 8.2, that's going to make it 820 is equal to the momentum of our skater, kilograms times meters per second. And here it's going to be 182 is equal to the momentum of our cone. Okay, guys, that's about it, because the last problem that we have is dealing with the inelastic collision. Okay, and that, ladies and gentlemen, is pretty simple. Okay, we got mass 1, velocity 1, mass 2, and velocity 2. Okay, they're going to crash into each other, and then that's going to be it. Okay, you're going to combine the masses, and I have to stop. Toodles.